Hello. So good day. Today we are going to uh, get into a very interesting session, and this particular session is going to be about the finite element modeling and simulation. It's a computer engineering simulation of a induced draft fan impeller, a radial impeller, and is used uh, in thermal power plants, especially under the cooling towers, where industrial gases from the lower atmosphere uh, is pushed into the upper atmosphere through the cooling tower, and it is sent outside. So these are all huge structures, especially in the range of 1.5 meter to 1.75 2 meters in diameter. And these structures can range anywhere between zero point 0.5 tons to about 3 to 4 tons, or maybe about 5 tons, depending upon the region where it is used or the application where it is used. So here we are seeing a particular induced draft fan impeller, which is almost about 600 to 650 kgs, the complete load, the weight of the system. And this is made of one of the steel alloys with excellent uh, structural as well as thermal properties. And there is a reason behind performing a application, I mean, a simulation like this, as one of the clients who wanted to understand the difference or wanted to do various studies about the impellers for their applications. So usually, most of these kind of impellers were all casted, and as casting, took most of their so casting has taken a lot of cost, and the client also felt that there could be further optimization done on this particular structure because the cost used to be high, and then competition also used to be high. So we had taken this particular assignment where we checked if the process of fabrication could solve the purpose. So we have considered the alloy, the CS245, I mean the MS alloy, the mild steel plates, plates, and these plates of a specific thickness were welded, fabricated together, and then we have arrived at a structure like this. The structure is subjected to about 800 RPM, so that's a good amount of rotation. And there is a central disc shroud that you see here, and this is where the shaft comes and connects. And we find the central disk, then we have the top disk and the bottom disk. We calculate the top stiffener and the bottom stiffness, and then we also have the top plate, the bottom plate, and we have the crown, the top crown, and the bottom crown. So these are the different parts of this particular thing, and individually each element was developed and then fabricated, welded. So this is a continuously fillet welded structure and tested, and now this is subjected to a rotational velocity of 800 rpm. So with a rotational velocity of 800 rpm, how does the structure behave? Whether these blades, whatever the blades we see here, the central, the top, bottom blades, all these blades are going to be stable. So initially we didn't have this particular stiffener, the top and bottom stiffeners. But what we found was the blade used to buckle, the blade used to break at higher RPM. So we performed optimization studies on this. We also performed a couple of iterations, structural simulations, and then we arrived at the suitable thickness for each element, and then we finalized on the system, and this was given to the customer. So this particular mentioned has a weight of about 600 680 kgs. So we have the mass properties here, okay, based on the density of the material. So we have 683 kgs, about close to 700 kgs, and we are going to perform. We are going to perform a suitable simulation onto this. So the suitable simulation, in a sense, it's again a structural simulation because we are not going to make it complex. We don't have to make it complex by performing, a CFD simulation at this stage. We just want to check for the structural integrity and the sustainability of the design. So this particular CAD model was imported into one of the tools, the final element tools, and then the system was meshed using TET elements. So we have taken tetrahedron elements, and the next to next optimization procedures. We arrive at we go for a better elements like hexahedron, brick elements, etc. for better results. So since the preliminary part of the analysis, we make use of TET elements, and tetrahedron elements, isoparametric elements are all stiffer in nature, and now, what we do is the particular shroud, the central disk, where the shaft comes and joins and couples. So we have bolts. These are 42 dia bolts, and we also have a member here inside the central disk. Okay, where we have the top and the bottom plates. Okay, based on the rotational velocity. So if the rotational velocity is increased from 800 rpm, say 2200 or 1500 rpm, depending upon the requirement, then there will be a top plate and a bottom plate connected to this, and then that will be bolted. So here in this particular case, instead of increasing the complete thickness of the plate, we have a top and a bottom plate which is bolted. So again, this is a 22 dia bolt, and based on the assumption that the bolts have got a axial rotation released, so we have 6 degrees of freedom for any constraint mechanism, three in the translation and three in the rotation. So now three in the translations are arrested, two in the rotations are also arrested, but one in the rotation is released, which is axial inline. So now, as we know that the shaft is connected at the center, and the shaft rotates at 800 rpm, and at 800 rpm, the blanket of air which is surrounding the shaft is going to be axially injected inside. It will take inside, and that is going to move inside radially. Okay, so there will be a centrifugal force, and radially through these gaps, the gaps that we see here, through these gaps, the air which is inline, that gets radially distributed. Okay, so that is the reason we call it as an axial impeller. Okay. So now we uh, do the meshing part, which is very important because only once the meshing process is done, we will be able to do the further simulation. So now what we do is we are meshing it using isoparametric elements. So this is how the meshing is done. And these regions where we have the weld connected, so we need to get the results in a very refined manner. So we have we have taken the curvature based blended algorithm, and based on that algorithm the meshing procedure is done. So this being, the initial part, even before the optimization. So this is the initial study. So where we take or we make use of the isoparametric elements, and then we apply the suitable boundary conditions to that. So we define that there are bolts of 42 dia and 22 dia respectively, and then we release it axially, and then we apply a load, a centrifugal load. So I mentioned that the shaft is rotating at a speed of 800 rpm. So it is exactly applied at the center, the axial inline to the shaft. Okay, and then we perform a simulation. So once we perform the simulation, we will be able to uh, get the values, the stress values. So once the simulation is done, performed, we notice that the stress and the deformations. Okay, so depending upon the structural, I mean the material property, depending upon the material property of the material. So this is the stress contour. We call it a stress contour, and here we have the von Mises stress. So we have different types of stresses. We have von Mises stress, we have Tosagi stress, we have Mohr-Coulomb stress, we have Rankine stress, okay, and we have Tresca stress. So these are all different stress theories, and based on the different stress theories, we perform the stress analysis. So usually the Mohr-Coulomb, Rankine, Tozagi, these are all stresses, the stress theories that we use for fluid structure interaction, especially anything related to ground or soil or foundations, especially in the geotechnical and the structural engineering part, we take care of it. And this is specifically from the mechanical systems point of view, we take the von Mises stress. And I don't want to get into the in depth of the technical part of the theoretical part of one Mises stress and all this. So here for today, let's just see how the simulation is done on the impellers. So these are the bolted locations, and these bolted locations will be able to find out the stresses are a bit higher, and these are the other regions where the possible stress areas. So here, this is the blade, the vertical blade, and then we have the stiffeners, the top and the bottom stiffeners, and along the top and the bottom stiffeners and the stiffeners, we'll be able to find that the values, the stress values are all a bit higher. Though it is higher here, we find that the yield strength of the material is only about 241.275 Newton per mm square. Okay, however, the maximum stress, okay, which possibly could be because of uh, localization. Because of the localization, we are able to achieve, I mean, we are able to get about 41.12 Newton per millimeter square. So, which means the system is safer. System is safer, and we have, good room to go up to 241. Okay, so which means I can decrease the thickness of every structure, and then uh, perform the simulation, and then later I will find that as and when I keep reducing the thickness, the optimization is done, the stress values will go up. So we can go up to 160, 170. Okay, but still we don't need to be that critical on these kind of structures. Okay, and let's get into the displacement point. So we'll find that, I mean, we found that the stresses are safer and it is very well within the yield strength of the material. So now let's see what is the displacement. I mean, how much deflection occurs in the blades. So this is the displacement plot. Okay, so now we find that the minimum deflection occurs at the central disk route because it's heavily, it's very thick, which is about some 22 mm in thickness. Okay, so that's the reason you find the blue contours here, so which is about, micron 0.006. Okay, but then the blade, the region where the stiffeners in between the central disk and the top stiffener and the bottom stiffener, we will find that the blade is deflected. So the blade deflection, the red color plot, what we see here, is about 0.06 mm. But still, that is along the safer zone. And towards the crown, the top portion of the crown, you will find it is almost around 0.02, 0.03 mm. So, which means this particular impeller is very much safe to take a load of 800 rpm rotational velocity. Okay, that is one way we can assume or predict. Now, or we can conclude, or what we can infer is from 800 rpm, the rpm can be increased to up to 1200 or 1500 rpm, and so that we can find out whether the system is going to be stable. Okay, so usually what we do is we don't try to improvise on the load. So maybe the existing structure, if the designer feels that the existing structure is over designed, and then there is a lot, there is a chance or a probability for optimization which can be done on it. So uh, that particular system will be used for a higher loading condition. Especially 800 rpm can be taken up to 1200, 1500 rpm, and this can be impeller itself can be moved into a different category, or the components inside the structure can be reduced in terms of its geometrical dimension, especially the thicknesses. And once the thicknesses are reduced, we'll find that the stress values and the deflection values will increase. Okay, that's quite obvious because the thickness is going to reduce, and as the thickness reduces, there are going to be a lot of bending stresses induced on the structure. There can be a lot of deflection that can occur because of that. Okay, so thank you very much for watching this, and I will also show you a specific video on result interpretation, because this is where people make a lot of mistakes. They interpret it in a slightly different way, or maybe totally in a different way, so that it becomes wrong. The inference will be wrong. So this is all about the impeller, and my next video I will make it more interesting with a computational fluid dynamics simulation on the same impeller. And whatever we see here, we can extend it into the next level. We can also find how the airflow, also the how the airflow is readily getting distributed from the impeller. Okay, thank you very much, and I request you to kindly subscribe and share this particular video, and I will also bring more interesting videos next time. Okay, so also feel free to comment and pass on your queries, and kindly have a visit on the website. You will be able to find more interesting materials there. Okay, thank you. This is Praveen Ramachandran Nair, founder and CEO of Baba Simulacts Private Limited.